So I think it's better to start. So today's lecture is mainly concerned on accelerated flight. So this accelerated flight is most of related with the maneuvering flight. So you can class as an accelerated flight or maneuvering flight. Many of our discussion, we concerned only steady level flight condition. But the actual flight is not only steady level flight, but maneuvering flight is also the part of the flight, especially those in the area where powered flight is taking place, especially during takeoff, during landing, again, during such turning and especially turning in the level as well as turning in the altitude. That means pull up maneuver, pull down maneuver, and also turning in the level. So there are different words actually. And they consider some acceleration. They need some G-force. G-force. In the level flight, all the forces are balanced. That weight is balanced with lift, thrust is balanced with drag, so that it is level flight or it is steady flight. But in the case of accelerated flight, we use excess power or excess thrust. So during using excess power or excess thrust, we need some G-force. Okay? So the flight is not steady during this time. And in such flight, we consider the N, that is load factor. Don't be away from what is it? Tagablaችሁ ተቀመጡ ለመራቅ ብቻ አትሂድ። ይኸው እዚህ ጋርም አለ። So upon the completion. So upon the completion of this lecture, you are going to analyze what is the aerodynamics of aircraft motion under non-equilibrium condition, because this accelerated flight is non-equilibrium condition. In this case, we have summation of force is equal to mass times acceleration. But in the previous case, most of the flights are considered in level steady level flight condition. And we are going to determine the resulting accelerations. And we are going to evaluate their impact on the climbing performance, turning capability, the load factor, and stall conditions. So these all are going to be seen with this topic. And to examine how an aircraft accelerate or change direction when thrust, drag, lift, and weight are not in balance. So changing direction is one of accelerated flight. Again, that the change in direction can be horizontal maneuvering or like banking, the case of. Again, it can be pull up or pull down from the high altitude. You are going to quantify how excess thrust or excess power contributes to longitudinal acceleration. Okay, so the excess thrust is also the part of lift during this moment. Evaluating the relationship between the bank angle and the load factor. Bank angle pi is there, load factor n is there, n is the weight divided by lift. No, lift divided by the weight. And you are going to assess the implications for turn radius. We have to calculate turn radius. The minimum turn radius is required. The maximum turn rate, omega max. We need minimum turn radius. Because if the aircraft is performing turning in very long radius, that means it takes time. So we need minimum turn radius as well as we need maximum turn rate. Turn rate is the rate of change of pi, the bank angle, so which is omega. What is the accelerated stall speed? We have to calculate the stall speed. So we know that the speed calculation is there. We have a radical of 2m over rho SCL. But in the maximum stall condition, we have CL max. We use CL max. But in this case, instead of only 2W, W is the weight, 2W, we add N, the load factor also. The load factor is the part of this. So our new stall velocity is in addition to the CL mass, this is the radical of 2 times of N, the weight over rho S CL mass. So in the accelerated flight, this is additional factor, right? So that is what we are going to see. So this is the type of accelerated flight. Okay. So when an aircraft in level flight at a given coordination X, Y, Z, that is kind of level flight. But in the case of accelerated flight, you can see the takeoff condition, the climbing condition, again, turning at the maximum altitude. Again, it can perform kind of banking also. So these all are under consideration. So accelerated flight refers to any condition in which the aircraft velocity or direction is changing. That means the net external force is not in equilibrium. The net external force is not zero. So to be in equilibrium, what happens? Summation of all force is equal to zero, or summation of all moment is equal to zero. When I say all force, maybe force in the X, Y, Z should be zero to be equilibrium. In addition to the three moments about X-axis, moment about Y-axis, and moment about Z-axis. Maybe you can consider the pitch, yaw, and roll moments are in equilibrium, which is equal to zero. But in accelerated flight, this may not happen because the summation of force and moments are different from zero because they are not in equilibrium. So in an accelerated flight condition, as you know, lift is equal to weight and thrust is equal to drag. So that is steady level flight condition. But in the case of accelerated flight, there is an unbalanced force which producing linear or angular acceleration. So our summation of forces equal to what? Summation of all forces, I forces, that I and B, X, Y, Z, is equal to mass times I acceleration plus summation of all moments is equal to it can be energy times and times the angular acceleration. Okay? So you have such kind of relation in the case of accelerated flight. So there are two types of acceleration: linear acceleration and angular. So linear acceleration is related with the linear forces, translational motion. And angular acceleration is related with the turning or rotational force. So that is what. In the case of linear acceleration, we have longitudinal acceleration, and we may have vertical acceleration also. It contains longitudinal as well as vertical acceleration. Okay, so the longitudinal acceleration, that is about the lengthwise of aircraft. What we consider is the length of aircraft from nose to tail of aircraft, right? So on that, you can consider the axis is called longitudinal axis. There are three axes of flight. One is longitudinal, another is lateral. From wingtip to another wingtip is called lateral direction. And there are vertical axis. Vertical axis is in the Z direction. Okay. If the lateral is considered Y and longitudinal considered X, then the vertical is considered in the Z axis, so that the forces that act along X axis or in the longitudinal direction is the longitudinal acceleration. So longitudinal acceleration occurs when there is an imbalance between thrust and aerodynamic drag. So if there is thrust is different from drag, what happens? There is longitudinal imbalance will happen. So we put the balance, thrust minus drag is equals to mass times acceleration. So thrust minus drag is what? Excess thrust. Thrust minus drag is called excess thrust. So that excess thrust is equals to mass times acceleration in the longitudinal or parallel to the longitudinal acceleration. So the aircraft accelerates forward in this case when thrust is greater than drag. Here we have maybe thrust minus drag can be plus or minus. It is plus, that means thrust is greater than drag. That means our aircraft is accelerating to forward. And it is minus when we are descending. When the aircraft is climbing or lifting up, thrust minus drag is positive. And when the aircraft is descending to landing, then what happens? Thrust minus drag is negative. That means thrust is less than drag. Okay, so the drag force in the opposite direction helps to lifting the aircraft rather than, so that is the meaning. And when thrust is equal to drag, that means the aircraft experiences no longitudinal acceleration and maintains the constant forward velocity. That is cruise state. The state is called cruise state. So the best example of the above is takeoff roll is powered flight. Ground go around is just spinning around, speeding up in the level flight. When you are changing velocity in the level flight, that also thrust is greater than, or the forward motion is greater than the drag. Another is vertical acceleration. So that arises from the imbalance between the aerodynamic lift. In the vertical direction, we have lift and what? Weight. When lift and weight imbalance occur, that means we are having vertical imbalance. Okay. So when the net force in the vertical direction is not zero, the aircraft will accelerate upward or downward, climb or descend. Okay. So you can see mathematically, summation of forces in the z direction is equals to mass times acceleration in the z. So what are the forces? Lift is there. The z component of thrust is also there. Look, so it's climbing, assume that this is the aircraft. So the aircraft is climbing like this. So lift is perpendicular to the surface anywhere. So the thrust also, the component of thrust also be part of our upward velocity. If you listen to thrust at the moment, this direction, one is enabling the aircraft to move in this direction, another is upward. So this is thrust in the Z direction. So lift plus thrust in the Z direction is equal to what? Mass times acceleration in the Z direction. So from that, you can calculate acceleration, the vertical acceleration of aircraft. That is lift plus thrust in Z direction minus weight divided by mass gives you the acceleration. So this vertical acceleration happens during when? It is during pull up or push forward, or it happens during climbing turn. While climbing, aircraft also tend to turn. direction change. Okay, that are the conditions. So these are some of. So if lift plus thrust in the z direction greater than weight, the aircraft accelerates upward. So the first picture indicates accelerates upward direction. When lift plus thrust in the z direction less than the total weight, that means the aircraft is descending, that is downward, accelerates downward. That means it's coming to land. And if these two components are equal, then aircraft is in a steady level flight condition. So that is the meaning. So angular or turning acceleration is another important. So it refers to the rate of change of an aircraft's angular velocity about one of its principal axes. So there are three axes: longitudinal axis, lateral axis, and vertical axis. There is roll, pitch, and yaw motions are there about those three axes. So roll axis, pitch axis, or yaw axis. So the roll will take place about its longitudinal axis. About aircraft longitudinal axis, aircraft will make rolling. Pitching will happen about its lateral axis. So it will pitch up and down, nose pitching up and down. And another is the yaw motion, which is about the vertical axis. Yawing motion, yaw means nose right and left, right? The motion of aircraft, nose right and left is called yawing motion. So that are the three motions and the three axes. So it occurs when unbalanced moment or torque acts on the aircraft. So this rolling, pitching, and yawing happen for rotational effect, that turning. So mathematically acceleration is equals to, so simply moment or torque is equals to I, the moment of inertia, times the angular acceleration alpha. So, and the angular acceleration alpha is equals to the net applied moment or torque divided by the moment of inertia. So you are familiar with what the moment of inertia in your previous courses, or even your aircraft structure, as well as strength of material and so on. Roll acceleration, pitch acceleration, and yaw accelerations are the type of acceleration and which aircraft control surface will involve for different kind of motions. One of the roll acceleration occurs when net rolling moment acts about the longitudinal axis. So rolling happen about the longitudinal axis, and how it rolls with the help of which control surface aileron will involve on the rolling action. aileron ምንድን ነው የሚያደርገው? አንዱ aileron ወደ ላይ ሲሆን አንደኛው ወደ ታች ነው አይደል? እንደነ ፍላፕስ አብሮ ከፍና ዝቅ አይልም። Right and left aileron operates in simultaneously. One is in upward direction, another is down. So by making that, the aircraft will roll about longitudinal axis. Another pitch acceleration is which results net pitching moment about the lateral axis. So that can be achieved with the help of stabilizer. So stabilizer is a combination of stabilizer and elevator. So the stabilizer and the elevator together perform action. So that are the control surface. And then yawing acceleration arises from the net yawing moment, which is about the vertical axis. So for that, the radar will take place. The one at the tail of aircraft, you have radar. So that radar will operate. So that are the control surface. So now these are the turning lights. Pull-up turning, that means when an aircraft is coming from some altitude, it reaches to minimum point and then goes to up. So it is also assumed that this is yours base. So this kind of flight, in this kind of flight, aircraft reaches to the minimum point here, sir. So that at that point, what will happen? Weight is here. Again, the lift is in the vertical direction. So such kind of, and also when it is just returning, it has another force which pushes the object outward. That is centrifugal force. Centrifugal acceleration is the downward because it is performing about some center in. Assume that this is radius. So for that, F centrifugal and we are there. Again, lift is in this direction, in this picture. In that, pull up manner. Pull up is from the minimum point. Push down by half this radius like this. When the aircraft is returning to down, that the second picture shows that it is pulled down manner. So during this time, what is that radius? The minimum radius required to turn or pull up or pull down. What is the angle, the rate of change of angle? Okay, that is what we call turn rate or something like that. ስለዚህ turn rate እና turn radius እዚህ ሰዓት ላይ ኢምፖርታንት የሆኑ ፋክተሮች ናቸው። So the pull up and pull down maneuver describes specific changes in an aircraft flight path in vertical plane. Look, during pull up and pull down, the aircraft is in its vertical plane. Our plane of motion is vertical plane. So that vertical plane will take place. But in the case of level turn, the turning takes place in horizontal plane. On some specific horizontal plane, it will take place like this. But in pull up and pull down, our plane of turn is here. Aircraft move like this, go up, and like that. So level turn and pull up and pull down turn are completely different. So you have to differentiate them. Okay? So in the case of accelerated climb or dive, actually accelerated climb or dive are also another maneuver flight type. So they need during accelerated climb, it needs excess thrust or excess power. During dive, it will operate in opposite. So an accelerated climb or dive occurs when the aircraft experience non-zero acceleration along its flight path, meaning the thrust to drag balance and or the flight weight balances, lift to weight balances, not in equilibrium, just as we have discussed before. An aircraft enters an accelerated climb when thrust exceeds drag. As you see in your thrust or the drag curve, the thrust required and the thrust available curve, there are regions where we are using excess thrust. Because on the curve, you have this kind of profile. So on that, if we have, this is the thrust available curve, this is thrust required curve, but still at this point, you have excess thrust. It's called thrust excess. So this thrust excess is for the climb flight. But during diving, the thrust is less than drag. Drag is exceed thrust during diving. So diving is another type of accelerated flight. So the net force along the flight path is mass times acceleration, as I said. So thrust minus drag minus weight sine gamma is equal to mass times acceleration along the flight path. Parallel shows along the flight path, parallel to the flight path. So here, gamma is the climb angle. So that is the meaning. So acceleration, climb acceleration is equal to how much? Thrust minus drag minus weight sine gamma over mass. So you can put, assume that this is climbing, right? Okay, as this is your flight angle gamma. So thrust is there, weight is acting down here. Okay. So this is weight. Again, you have a thrust direction here. Okay. So when you resolve this force to this and that, so you have here. Okay, so this is thrust. No, this is weight. Weight. This is gamma. Weight sine gamma. And weight cos gamma. So by recording that, we have the sine gamma part is along the flight path. You see, weight sine gamma is along the flight path. So thrust is there, drag is here. Thrust drag is here. So thrust minus drag. This is in the drag direction, right? Minus weight sine gamma equal to mass times acceleration along the flight path. That is the meaning. So, what are the key characteristics of accelerated climb or dive? One is the aircraft does not maintain steady level flight. That is one of the parameters of steady climb or steady dive. Energy increase or decrease. When it is climbing, energy increase. And when it is diving, it decrease. The flight path angle and the velocity change simultaneously. Both of them change simultaneously. Both longitudinal forces and vertical forces determine the motion. So if the climb is steady, then acceleration in the x direction is 0. And if the climb is accelerated, then the excess thrust becomes partly involved in the acceleration. So that the mean. So now let's start with level turn. Start with level turn and derive some formulas which are helpful for level turn. So the flight path and force for airplane in the level turn are, you can see the sketch. One of the view is from the top. So the circle which you are looking is on the top. When you see it from the top, the aircraft is performing a turn, but still the aircraft is in the same altitude. It will not increase altitude or decrease. Okay, so level turn is related with flight within the given altitude only. Okay, and another is when you see the aircraft from the front. So the front view and the top view of the aircraft is there. So level turn is one in which the curved flight path is in horizontal plane. So look, this is vertical plane, as I told you, because you can pass change in altitude. So this H1 is different from this H2 in this case. But in the level turn, assume that this is the flight path, this is center. Again, you have some reference altitude. So everything in this distance H1. So assume that this is ground. This is ground. And this is the point where an aircraft is circling, just moving. Everywhere, if I stretch this point to here, this is H. This is H. This is also H. So everywhere it is in H altitude. Altitude is constant. Where the aircraft is performing banking, just direction changing without increasing or decreasing the altitude. So that's what we call level turn. So in level turn, the altitude remains constant. Altitude remains constant means what? DHDT, that is rate of climb, is equal to 0. DHDT is what? Rate of climb. So which is 0. And the airplane is banking through the roll angle pi. It is just performing roll angle pi, a small banking angle with the aircraft with horizontal reference. So that pi is just rolling angle. So the vertical component of force, which is for such case, it is L cos pi, which is exactly equal to the weight. In this case, the weight is acting downward, and the lift is the L cos, lift cos pi. So what is the look, lift is in this direction. We have y-axis, x-axis here, and weight is here, weight, and lift, and it performs pi angle. So you can resolve this into vertical and horizontal. So the vertical component lift about this adjacent, it is cos pi. Okay. So W is equal to L cos pi is the level turning condition. Level turning condition. So that is, look, that is the circle where an aircraft is just circling on the top at a given altitude. So while it is leveling there, what happened? There is a centrifugal force in the outward direction because there is centripetal acceleration down to the center, right? For that, there is centrifugal force. That is mv squared over r is there. So in the horizontal direction, look, this is L cos pi, and this is L sine pi. So for this force, this force will this force about this point, right? And then in this direction, what we have is the force that resists this force. That is mass times acceleration in centrifugal acceleration, that is v square over r. M times v square over r is that direction, and this direction L sine pi. So that will balance. So L sine pi is equal to mv square over r. R is what? The turn radius. R is the turn radius, v is the flight velocity, and L is the lift. So M is the mass of the aircraft, so that you can convert it to weight. So mass is equal to weight over gravity. And the vertical component is L cos pi is equal to W, as we have discussed. And from the load factor is defined as the ratio of lift of aircraft by the weight. Lift divided by weight is called the load factor. And from the second equation, cos pi is equal to what? Weight over lift. Cos pi is equal to weight over lift. So that N is equals to load over lift over weight. So that it is 1 over cos pi. Load factor is equal to 1 over cos pi, directly from the second and third equation. So from that, you immediately find the turn radius. Turn radius is equal to v square over, from where? Substitute this thing to there. L sine pi is equals to m. So change m by weight. So that is weight over gravity is there. So finally, simply substituting those equations, find what you can get. R is equal to V square over G times radical of N square minus 1. እንዴት ይመጣል ልትሉኝ ትችላላችሁ። ይሄ ኤን ስኩዌር ከየት መጣ ምናምን የምናየው ይሆናል። It is easy actually. ስለዚህ አንደኛው ምን ሆነ? ሌፍት ፎርስ አይ ኢኳልስ ቱ ምን ሆነ? ዌይት ሆነ አይደል? ስለዚህ ይሄ ምንድን ነው የሚሰጠን? ፎርስ ባይ ኢኳል ቱ ዌይት ኦቨር ሌፍት በት ሎድ ፋክተር ኤን ምንድን ነው? ሌፍት ኦቨር ዌይት ማለት ነው። ይሄ ማለት ነው የዚህ ዋን weight over lift ማለት ነው። ይሄ ማለት ደግሞ ማለት ነው over n one over cos pi ማለት ነው። cos pi ስለዚህ cos pi is equal to 1 over n ማለት ነው። cos pi is equal to 1 over n ሌላ ምን አለ? እስቲ ይሄን እንደ አንድ ነገር ያጣል። ሌላ ደግሞ ሊፍት ሳይን ቲታ ሊፍት ኤል ሳይን አይ ሪኮርስ ምን ብለናል? ወይት ብለናል። ሶሪ ሊፍት ኮስ ቲታ ከዛ ከመጣው ሌላ ደግሞ ሊፍት ሳይን ቲታ ሳይን አይ which is equals to and V square over R. Right? Here n sin pi is equals to weight over gravity V square over R. Here then ስለዚህ ያ ገባህ ሌላ አንድ ትሪጎኖሜትሪክ ሪሌሽን ጋር ትሄዱ ምንድን ነው የምታገኙት? ስለዚህ ከዚህ የምታገኙት አር ኢዝ ኢኳልስ ቱ ዋት? አር ኢዝ ኢኳልስ ቱ ዌይት ኦቨር ጂ ታይምስ ቪ ስኩዌር ኦቨር ኤን ሳይን ምንድን ነው ፓይ ሶ ዳት ሚንስ ዋት? አር ኢዝ ኢኳልስ ቱ weight over lift ምን ብለናል? weight over lift ምን ብለናል? cos pi ማለት 1 over n አይደል? ስለዚህ እዚህ ጋር weight over lift አለ። ስለዚህ 1 over g times n አለ እዚህ ጋር times ምን አለ? v square over sin pi እዚህ ላይ ከደረስን ኋላ ማለት ከትሪጎኖሜትሪ ሳይን ፓይ ሳይን ስኩዌር ፓይ ፕላስ ኮስ ስኩዌር ፓይ ኢዝ ኢኳል ቱ ዋት? ትሪጎኖሜትሪ ላይ ያለ ትሪጎኖሜትሪ 1 ስለዚህ ኮስ ፓይ ኦኬ ሳይን ፓይ ስኩዌር ፕላስ ኮስ ፓይ ማለት ማለት n square equals to 1. So sin pi square pi equals to 1 minus 1 over n square. So that means n square over n square minus 1. So sin pi equals to radical of n minus 1 over n square, which is radical of 1 over n divided n minus 1 So here substitute now. 1 over NG times B square over radical of N square minus 1 over and those go ahead and so which is equal to B square over what G times radical of N square minus 1. So that is the R. So turn radius, the level turn now. The turn rate again, turn rate means what? It is omega. Omega is equals to velocity over V over R. Omega means per second, rad per second, something rad per second, unit meter per second divided by meter gives you meter by cancel by meter, you have left per second, rad per second. So velocity divided by R gives you omega. So when you do that, what you can get is G over N square minus 1 over V is the turn radius. No, the turn rate. Is it okay? So where psi is the turn angle, then the turn rate is simply the local angular velocity. So omega is equal to psi dot. If you consider psi as the turn angle, then it is psi dot, and which is the local angular velocity of the airplane along the curved flight path. That is the meaning. So already again discuss same thing which you can obtain from here is radius is equals to V square over G radical N square minus 1. So that turn radius represents what? The turn radius depends on flight velocity. Look, from the equation itself, the turn radius depends on what? The flight velocity. Another factor, it depends on what? N, the load factor. So that are the factors which can affect the, so our intention is to minimize turn radius. If turn radius is larger, we are going to fly throughout the city, okay? To land, or if the aircraft is making loitering action in the Debrezhite city, and if the turn radius of aircraft is too much larger, then it can wander around the city. So it is better to minimize the aircraft design to minimize minimum turn radius. So for that, the higher velocity is higher turn radius, right? So velocity should be lower. The higher value of n, the maximum n, then turn radius is minimum, right? We are dividing the velocity square by n factor, right? G is constant. G is constant for a given altitude, so that the two variables which matters during this time is V and N only. So V should be small, N should be higher. So our intention is to find maximum N value, the maximum N value. So N max is required. There also, we need higher omega. Omega max is required. In order to get omega max, V should be small and N should be maximum, right? Minimum radius, maximum omega, turn radius, or turn rate. So these are requirements. Okay, so the highest possible load factor, N max is required, which is the highest possible L over W. We are familiar with lift to drag ratio, maximum lift to drag ratio, but now here lift weight ratio should be also maximum for appropriate turning. And the lowest possible velocity, V minimum, is required. V minimum combination with N maximum will provide us an appropriate turning. Okay? So the maximum possible load factor, N max, should be now in this case. And how we can get it? From the drag polar equation, simply take the drag equation, and for the level term flight, L is equal to N times W. Now, in our previous case, in steady level flight, L is equal to W only, right? But now, L is equal to what? N times W, because N is equal to L over W. So the lift is now, the lift equation, half rho V square SCL. So NW is equal to half rho V square SCL is the equation. So this is the new equation for accelerated flight condition. So your CL becomes what? 2NW over rho V square S. So N is that the load factor. And the thrust is, in this case, considering thrust is equal to drag condition for the thrust required. Now, this is not exactly the thrust, but the thrust required is equal to drag. So that thrust required is half rho V square S CD, and just substituting the CL value, you can find the N value. So that N value is directly from the above equation. Okay, so there you can make some small rearrangement for the equation. Okay, so N max is this equation. The maximum N is our important factor. So maximum N is equal to half rho V square, that is Q over K times wing load. W over S is wing load, the whole within the radical T over W max condition. Load factor maximum, T is instead of lift. So T over W max minus Q CD naught over the wing load. So this is the maximum N max condition. So for a given V velocity, the N maximum load factor can be in the range of, it is greater than 1, and N should be with some maximum value. It should not randomly taken. Okay, so we have to limit that N max. N maximum should last it has also a limit. So N max is dictated by the design parameters, that W over S, that W over wing load, thrust to weight ratio, the aerodynamic coefficient CD naught and K, as well as in density. So these are some of the factors. Yeah, you can see them zero on the equation itself. So we can also find this thing from the directly using the conventional method. N is equivalent with L over W. So on that you can multiply by drag and divide by drag. L over W is there, just multiply it by drag over drag. So that gives you L over D, lift to drag ratio, to get CL over CD max condition, and thrust over weight ratio also there. So L over D is there. In order to get maximum N max, thrust to weight ratio should be maximum. Thrust to weight ratio should be maximum. So from that diagram, you can find the limiting point. There is a limiting point for this. So N max is equals to N points. Actually, there are points A, point B, point C, point D in this graph. Gives us some different values. So this condition will limit us not to go further. So N max is Q times CL max the limiting load is, load factor is half rho v square, that is q, times CL max divided by wing load. CL max divided by wing load. Q times CL max over wing load limits the N max condition. The largest possible turn radius, as I told you, our intention is to get N max and omega max, but R should be minimum, right? So the largest possible turn radius for omega max, which is psi max, we can obtain from the equation of the omega. So omega is equals to G radical of N square minus 1, the whole over V, or the flight velocity. So the highest possible load factor, N max, is required in order to get maximum omega. N should be maximum. In order to get omega max, the lowest possible velocity is required, V minimum. V minimum, that is, among the given, we have actually different types of velocity. Minimum velocity, maximum velocity, velocity at thrust required minimum point, stall velocity, and so on. So these are exactly the same criteria for the smallest possible R. So this is, so the constraint on N, V also should be constrained, not only N constraint, but V should be also constrained. So we have to fix the V value. We cannot randomly take V. R and W depends on the turn radius, and the turn rate are dependent on velocity and N only. Therefore, V and N should not be any arbitrary value. It should be some prescribed value or design value. So for the high performance, this equation dictates that N should be as large as possible. There are definite limits on the values of N that are associated with the design aspect. So for high performance, the velocity V should be as small as possible. In order to achieve low turn radius, velocity should be small. So these are actually theoretical aspects. So now let's calculate the smallest velocity. So V stall is the one of the smallest velocity, but still we can modify that. So V stall is equal to 2 times rho, 2 times omega times N divided by rho SCL max. So that is the stall velocity equation, because we are familiar with it. So now the stall velocity, this is equal to radical N times the V stall of the unaccelerated V stall of unaccelerated. For level 5, you have velocity, stall velocity. So now simply it is radical of that. So how we can determine minimum radius? Minimum radius determination is required. So in order to find the minimum radius, we have to set dr dv. We have to differentiate the radius equation with respect to velocity. Radius with respect to velocity. So the radius equation is given v square over g radical n square minus 1. Is it v square now? V now? Guys, v now R. Is R with v square? Yeah, v square. So just taking that radius equation and differentiate it with respect to velocity and equate it to 0. Finally, what you can get is that minimum radius condition. Now, minimum condition, what you can do is you have to differentiate. The mathematics lab. So that is here. So V means half rho V square. So that substitute it there. Finally, what you can get is 2 times Q. Q is half rho V square now. ስለዚህ አሁን ደግሞ with respect to Q ነው differentiate የምናደርገው አይደል? V is a factor of Q. So you have to differentiate it with respect to Q in order to get R minimum. So differentiate ስታደርጉ መጨረሻ ላይ የምታገኙት what? Already I followed stepwise mathematics. So finally, n squared minus 1 minus Q n dq is equal to 0 is the final answer. So here we have dn over dq is there. So we have to find this thing also. Okay, we have to find this thing. So n equation is given there. If you remember the n equation above, so that is n is equal to under radical half rho v square over kws. So whole times t over w minus half rho v square cd naught over w over s or wing load. So that for the maximum n, t over w should be t over w max. Don't forget, here it is simply n, but for the maximum n, what will happen? T over w is maximum, right? So n square means we square everything there in the square bracket. So we have radical there, so the radical will go. What left? N square is left. So you can directly substitute that n square here in this equation, n square minus 1 minus something. So substitute instead of n square this equation. And then differentiate that equation number 16, the n square equation. Differentiate it with respect to what? Q. Differentiate it with respect to Q. What you can get is some n times dn over dq, which is equals to thrust over weight over 2k times wing load minus qcd naught over k wing load square is the final of that 16 equation differentiation. So now, instead of n dq, you can substitute that equation again. Look, n dq. Instead of that, you can put it. Instead of n square, you can directly apply the n square there. N square is of the 16. So apply 16 and 17 to this equation. Finally, what you can get is, this is the equation. So just simplify this. Once you simplify this, finally what you can get is Q is equals to 2k wing load over T over W. So that Q means half rho V square. So just substitute those things. Finally, you can get V. This velocity is the minimum velocity. This velocity is the minimum velocity for R minimum condition. V minimum. It is called V minimum rather. So you can call it as V minimum over this. V velocity for R minimum condition. So that is the velocity constraint now. We constrain our velocity of the minimum for obtaining minimum radius is radical of 4k wing load divided by rho times thrust to weight ratio. So this is the minimum velocity required in order to find maximum turn radius and in order to find minimum turn rate, maximum turn rate and minimum turn radius. Is it clear? ግልጽ ነው? Okay, so now we have to also find n2 minimum turn radius. So that n is 2 minus 4 kcd naught over thrust to weight ratio square under radical. That is the n for minimum turn radius. V for minimum turn radius, n for minimum turn. N for minimum turn radius means what? N max. ከታርን ሬዲየስ ጋር ኤን ኦቨር ነው አይደለ? ቪ ስኩዌር ኦቨር ራዲካል ኦፍ ኤን ስኩዌር ማይነስ ዋን አይደል? ስለዚህ ያ ማለት ኤን ማክስ ኮንዲሽን ፎር ሶ ቪ ማክስ ኤን ማክስ ዋን ነው ኤን አር ሚኒመም which is radical 2 minus 4 ACD naught over TW, T over W squared. So by substituting that in minimum to R minimum condition, finally what we can get is the minimum turn rate. No, the minimum turn radius is 4K W over S divided by G rho thrust to weight ratio times under radical 1 minus 4K CD naught over T over W square. So this is our minimum turn radius. The same thing, so this is just a revision. This is just a revision. Velocity for maximum. Actually, the same process we can go to find velocity of maximum omega, n for maximum omega, and omega max. Omega max equation is Q, half rho V squared times radical of rho over wing load. The whole times T over W divided by 2K minus CD naught over K 1 over 2. That is under radical. Only CD naught over K is under radical. So these are the important questions. The next part is pull-up maneuver. So the pull-up and the pull-down maneuver. In this case, especially during the pull-up maneuver, an aircraft reaches to the minimum point and then it is falling up or flying up. So at the moment it passes this point, what you can see at theta 0, weight is acceptable, lift is perpendicular upwards, and the centrifugal force is acting downward. So, and the radius is so just theta is a very small angle, so that it will come up with the calculation. So force is equal to lift minus weight times weight times n minus 1. So the final, after some rearrangement, what you can get is R is equal to V square over G times n minus 1 now. In the free base, it is G times under radical n square minus 1. Aral, kadam? Ahunda mo G times simply n minus 1. So ahunim bihon, nazi negaroch. In order to find minimum turn radius, he should be minimum because the radius and velocity are in line actually. But n is in the 1 over n condition. So n should be maximum, v should be minimum. That is the meaning. Again, the turn radius is equals to also g times n minus 1 over v. So ከቅድሙ የተለየው ምንድነው? n minus 1 ቅድም radical of n square minus 1 በመሆኗ። ስለዚህ ታርን ፍላይት እና ይሄ የተቀራረቡ ነገሮች ናቸው። ኦኬ So the pull-up maneuver involves the aircraft climbing sharply from the level flight and creating a circular flight path in the vertical plane. It is in the vertical plane. The previous is in the horizontal plane, as I told you. So in pull-up maneuver, the change in angle of attack of the aircraft may be related with the lift coefficient. Okay, angle of attack and lift coefficient will come together. How they relate? We can see it. The pull-up with constant velocity, the angle of attack of the whole aircraft will be changed. Okay, alpha is changing. Since the aircraft has to fly at higher lift coefficient. ምን ይሆናል? መጥቶ እንደዚህ ሆኖ ወዲያው አቲቲዩድ ቼንጅ ያደርጋል። ስለዚህ ሲኤል ኢኳልስ ቱ ሲኤል ሊፍት ኮኤፊሽንት ሲኤል ኢኳልስ ቱ ሲኤል አልፋ ታይምስ አልፋ ማይነስ አልፋ CL alpha ማለት the slope of lift curve. The slope of lift curve is called CL alpha. DCL over D alpha, right? So CL alpha times alpha minus alpha naught. Alpha naught means the angle of attack at zero lift. Angle of attack at zero lift. Zero lift means when it is crossing the alpha axis. Which one is from? This is the most synchronized, you know. So this is your lift curve. Assume that this is your alpha, and this is your CL. So no, zero. በነገራችን ላይ እንደዚህ አይነት ስቴጅ ይኖራል። with geometry ላይ ይመጣል። ኤክስፒሪየንስ ከሆነ ይሄን So what is here? There is alpha value. This is called alpha naught. CL is 0 here. So alpha naught means alpha at CL is equal to 0. Alpha is somewhere the point where our aircraft is flying. So you have this CL alpha, which is D CL over D alpha. So the line equation of this thing is CL is equal to that Y is equal to AX plus B CL times. This is kind of CL alpha times alpha alpha minus alpha. Because alpha is CL in the negative direction. Anyways, C minus times. So that gives us the relationship between CL and alpha. CL and alpha are now so. So the pull down maneuver, also called dive maneuver. So that is another case. Now our aircraft is in inverted position. The aircraft is in inverted position. Especially the fighter aircraft can perform this. Maybe this is not possible for the passenger aircraft. So in the inverted position, lift is downward, weight is downward. The only force that suspend the aircraft is the centrifugal force. At the moment in time, the centrifugal force is pushing it outward, right? So FC, which is mass times V square over R. So you can equate it, and finally what you can get is R is equals to V square over G times N plus 1. Look at the difference. The previous N minus 1. Right? Now it is N plus 1. And omega is also G times N plus 1 over V square, because it is V over R. Omega is V over R, so that you can put the R value on the B, finally you at G minus N plus 1 divided by velocity. So that is the rate is imposed on the radius is enlarged over full arms. ስለዚህ ምንድን ነው n plus 1 ሲሆን n ማክሲመም እንዲሆን ነው የምንፈልገው። ሰው ምን ሆነ ማለት ነው? ጨመረልን ማለት ነው በዚህ ጋር። እዛኛው ላይ ግን ማይነስ you can observe, okay, n minus 1. So these are the pull up and pull down manner. Limiting case gas and meta. Yeah, just these are the summaries. In the level term, R is equal to V square. Yeah, you can observe them. Okay. In the limiting case, for large load factor, if the load factor is given large value, which is too much greater than 1, the three quantities which we explained are reduced to same form. ሶስቱም ወደ አንድ ነበር። ለምሳሌ በቃ ዋንን neglect አደረግ ነው ማለት ነው። If we neglect one from them, radical of n square is n also. N minus 1 is n. N plus 1 is n for the large value of n. So you can use that. So, and during that time, what is R? For the command for level term, for pull up, pull down, the same equation will come. Same equation. So V square over G times N. So on that, how we can relate velocity with lift from the lift equation. From the lift equation, you can relate velocity. So instead of velocity, you can put the lift equation. That is, because V is equal to V is equal to V square is equal to 2 times N theta, no, N W, rho S C. So you can put this on that equation. R is equal to what? R is equal to V square over G. And so put this 2 times N W over rho S C L G times N. So N becomes by N, you have left out. Also, that weight is equal to lift also will come. If lift is not in there, lift up and one comes in parallel. Yeah, this is parallel and weight for the so the weight for the it is 2 times weight over rho SCH over 2 times the wing load divided by rho S rho CL is the R value. Realization minimum weight is equal to N is equal to lift over weight kilogram. So weight is equal to lift over N. Now, ስለዚህ ይሄ እዚህ ጋር ደግሞ ኦቨር እዚህ ጋር N over W is N, right? Yeah, lift by lift ካላጠፋነው በስተቀር ምንድነው lift over weight is N. So N equals to 2 times lift over rho S here times N. So this N is lift over weight. ስለዚህ ከኔ ጋር ናቸው። ሰዓት ስንት ነው? ሁለት ከሀያ ሄዷል። ሶ እነዚህ አር ሚኒማ ኢን ዘ ሊሚቲንግ ኬስ 2W rho GCL max S. That is for R minimum we use CL max እዚህ ጋር በሊሚቲንግ ኬስ CL ማክስን ነው የምንወስደው። ኦሜጋ ማክስ ደግሞ ሲሆን still we use CL max N max. CL max N maxim in the maximum condition by limiting case. So half rho B square CL max over wind load ቅድም ያልነው እዚህ ጋር ይመጣል። So that is the meaning. Okay. ስለዚህ አንድ 10 ደቂቃ ሄድና another important is the VN diagram or the flight envelope. Flight envelope is one of an important aspect in this course. Still, what we have learned is about we didn't consider the structural problem in we already given attention only for the aerodynamics, right? So aerodynamics performance, velocity, but we didn't see what is the structural problem, how we can relate our course with the limiting load, the ultimate load, the limit load. So that is not yet discussed. So the VN diagram or the flight envelope is a unique chart. It is just a unique chart for each aircraft. The aircraft manufacturers produce the unique chart for each aircraft. And the aircraft operators will not exceed that point. They must obey that chart. So that most of the charts are going to be agreed by the Federal Aviation Authorities. So the VN diagram or sometimes you can say VG diagram, because the N indicates that how much G we are flying. Okay, so the chart is usually included in the aircraft flight handbook in the section dealing with operational limit. That it is in the Federal Aviation Authorities handbook. So this VN diagram presents the most important general feature of diagram. So what are those general features? Let's see. Look, this is the flight envelope. So I think it is better to make you kind of having የሆነ ወደ ዩቲዩብ ነገር ላይ ሄደን የሆነ ነገር ብታዩት ማታም ስለሆነ ፊልም ስታዩ ደስ ይላችኋል። So this is just VN diagram. ከዚሁ በደንብ ብታዩት
Hello, and welcome to JXJ Aviation. In this video, we will be looking at what is a VN diagram and why is it important for an aircraft. What is a VN diagram? A VN diagram is a graph between velocity and load factor.
Velocity.
This graph has
horizontal velocity, vertical
load factor on the y-axis and gives details about an aircraft's operating strength. Each aircraft has its own VN diagram for a certain weight, configuration, and altitude.
Weight, configuration, and altitude are important parameters.
What is load factor? Load factor can be defined as the ratio of lift to the weight of an aircraft. When an aircraft is in flight, the structure is subject to different loads. Limit load factor is the maximum load factor until which an aircraft is designed to operate. The strength of an aircraft and the materials that are used for building the aircraft depend on this load factor. The VN diagram. These curved lines are the maximum positive and negative lift capabilities of the aircraft. For a particular aircraft speed, the load factor cannot be more than this G value, because the aircraft will stall. This vertical line
So that
represents the
blue
maximum
line,
speed at
that
which the
line
aircraft
indicates
is
stall
designed to fly.
limit.
This speed is called the limit airspeed.
This green line is the speed limit.
Beyond this speed, there will be structural damage on the aircraft. These horizontal lines are the positive and negative limit load
Limiting
factors.
load factors.
An aircraft experiences a positive load factor when the lift is acting upward, and the aircraft experiences a negative load factor when the lift is acting downward. If an aircraft is flying in this speed range, and if the positive load factor exceeds this value, there will be structural damage on the aircraft. If the load factor increases further, it will lead to complete
If
structural
it
failure.
increases further, the structural damage will happen.
Beyond this negative limit load factor, there will be structural damage, and if the load factor drops further in the negative range, it will lead to complete structural failure. This point is called the maneuver speed of the aircraft. This is because, below this speed, there will be no structural damage to the aircraft while performing different maneuvers. This region is called the safe
Safe
envelope of the
envelope
aircraft.
is that region one.
The aircraft must be operated within this envelope to prevent any structural damage. In modern aircraft, because of the fly-by-wire technology, protections are provided in the auto-flight system, which do not allow the aircraft to exceed this safe envelope at different speeds and configurations. Thank you for watching.
Anyway,
If you
this
like
is
the
very
video,
short
please
video, but it gives you a clear idea about the flight envelope. So this is our flight envelope. So you can draw this flight envelope for the negative and positive case. So look. This line is the load factor n values. So it is intersect at 0. So this line indicates the aircraft speed in kilos or mile per hour. It can be meter per second. Any kind of unit can be. So the above parts indicates the positive limiting factor condition, the negative limiting factor condition. So each of the points are meaning. Okay. So one cannot go beyond. For example, if I fly with this speed, if you project the point to that A, it gives us same speed as every point. But n values are different. N values are different. But the speed is same. If I fly with this point, from here to here, same velocity. Velocity same, but load factors are increasing. So that is what. This line, the current line indicates the maximum positive lift capability. That is relative stall speed. So positive stall limit and negative stall limits are the stall limits. The maximum for velocity, the aircraft should never exceed this velocity, whether negative or positive. The maximum limit of speed is limited there. Again, there are horizontal lines, this one and that one, gives you the positive limit, the negative limits. So beyond the flight beyond this point, this horizontal line, to harvest to zero upward provides structural damage in the structure. Further increase in the N value, further increase in N value than that positively factor structure. Finally, structure failure. Damage and failure are two different situations. Damage is maybe initiate, propagate, and finally go to what? The ultimate failure. Failure is a collapse of structure. But damage can be solved by. Anyway, so this kind of restrictions are so aircraft must fly within the given same within the given distance. So we should never exceed the aircraft n value. We cannot use arbitrary value for n. So n value should be within a given limit for the structural, for the speed, and for the aerodynamics also. So the stall regions here, the harmonic current and are stall regions. So that is aerodynamic characteristics. That is structural characteristics, and this one is the speed. So all must be within the given limit. Unless the aircraft will go to a kind of undesirable condition like buffeting, like what you call that? Other excitation case. So we must operate the aircraft within the given limit. So that is the VN diagram. So you see, this is the stall region, positive stall region and negative stall region here. Okay. So Vs is determined here at point A. So stall point. Maneuvering speed. Okay. This is the limiting load region. So still the blue line indicates a fully safe region for the flight, but the red lines indicate the structural damage loads. Going the speed beyond the given speed limit will lead to structural damage. Using an appropriate amount of N will lead to also structural damage. So the aircraft strength is dependent on 4 factors. One is the aircraft gross weight, the total weight of aircraft, the aircraft configuration, that is the external stores, flaps, landing gear locations, the symmetry of loading, and the fourth one, the flight altitude. So through the density, the flight altitude also another factor. Yeah. ደክሟቸዋል። በቃ ነገ 4 ሰዓት እንገናኝና ይህንንም ፓርት ጨርሰን ወደ እንትን እንሄዳለን። ኔክስት ዊክ የሆነ ነገር ለመጨረስ እንሞክራለን። መቼ አንድ ቴስት ይሰጣችሁ? ይህን ሳምንት ጨርሳችኋል? ዛሬ ኔክስት ዊክ ምን አላችሁ? ይህ ፋይናንስ ስለደረሰ ያስጠላል። ለዛ በኪው ሰበብ ታጠናላችሁ እንጂ አሳይመንት ብሰጣችሁ ጥሩ ነበር። በአብዛኛው ሰው ፊት ሳየው የደከመ ይመስላል። ለዛ ነው የሁላችሁም ሀሳብ ነው? ኧረ አልክም ብዙ አለ ብዙ አለ። ኤግዛምፕልም አለ ይላል። ኦኬ እንጨርሰው ይህን እሺ፣ ይህን እንጨርሰውና እንቀጥል። ሶ these are structural limitations actually on the maximum load factor, and the structural limitations were not considered in the previous whatever we have discussed. Therefore, now we consider the G load or the N load. G load ማለት gravity will have influence on the aircraft. እስካሁን የግራቪቲን ኢፌክት እንትን አላለም፣ ግን አሁን የግራቪቲን ኢፌክት ጭምር ኤርክራፍት ባንክ ሲያደርግ ታርም ሲያደርግ ፑል አፕ ፑል ዳውን ሲያደርግ የሚያመጣውን ኢፌክት ነው። በነገራችን ላይ አንዳንድ ኤርክራፍቶች አንስቴብል እንዲሆኑ ተደርጎ ዲዛይን ይደረጋሉ። ስፔሻሊ ፋይተር ኤርክራፍትስ አር ዲዛይንድ ፎር አንስቴብል ሲቹዌሽንስ ዳትስ ዋይ ዴይ ካን ኢዝሊ ማኑቨር። ኮመርሻል ኤርክራፍቶች ደግሞ ስቴብል እንዲሆኑ ብቻ ተደርጎ ነው ዲዛይን ይደረግ። ትንሽ ሽፍት ካደረገ ምንድነው ኢት ዊል ኢንካውንተር አንባላንሲንግ ራይት። ሶ ኤኒዌይስ ሊሚት ሎድ ፋክተር ቅድም ያየ ነው። እንደገና አልቲሜት ሎድ ፋክተር የሚባሉ ፋክተሮች አሉ። So in the limit load factor boundary, which is boundary associated with permanent structural deformation. So as the force applied on the structure will encounter permanent deformation, the deformation which will not regain back. So one or more parts of the airplane will face permanent deformation or damage. If N is less than the limit load factor, the structure may deflect during maneuver, but it will return because it is elastically deformed. Permanent deformation is different from elastic deformation. The permanent deformation is related with plastic deformation. Okay. So at the moment N is equal to 1, it is still elastically deformed. If N is greater than the limit load factor, then the airplane structure will experience permanent deformation. That is, it will encounter structural damage. The further damage on the structure, ultimate load factor is the boundary associated with outright structural failure. That is beyond ultimate. Sigma stress strain diagram ወይም load displacement diagram ላይ ልክ ይሄ ቴስት ስፔሲመን የተጠቀማችሁት አለ ልክ እንደዛው ማለት ነው። ultimate load sigma ultimate is when it is in the greater position, that means almost the structure going for failure, like in the zone እዚህ ጋር so the aerodynamic and the structural limitations for a given aircraft are less. So እዚህ ጋር የምታዩት በነገራችን ላይ ፖዚቲቭ እና ኔጌቲቭ ስንል ኖዝ ፒች አፕ እና ኖዝ ፒች ዳውን ኮንዲሽን ነው እያልን ያለ ነው። ሶ እያንዳንዱ ፖይንት የተለያየ ስም አለው። እዚህ ጋር እያንዳንዱ የተለያየ ስም ነው። So Venn diagram is a type of flight envelope for a given plane. It establishes the maneuver boundary. Our maneuver boundary should be established. So እያንዳንዱ ፖይንት እዚህ ከርቭ ላይ ስም አላቸው። So n max ከቅድም ኢኩዌሽን ምንድን ነው? Q times L max over wing load ብለናል አይደለ? n max. So that n max should be limited. n maxን ሊሚት ማድረግ መቻል አለበት። ቬሎሲቲ ግቨን ቬሎሲቲ ደግሞ እንትን መደረግ አለበት። ኦኬ ሌላ ስቶል ሪጅን አለ። ስቶል ሪጅን በምንድን ነው የምናየው? the region above curve AB in the Venn diagram is stall region. curve AB እዚህ ከርቭ ላይ ከኤ ተነስቶ ነው ኤ ማለት እቺ ፖይንት ነች እስከ ቢ ድረስ ስቶል ሪጅን ተብሎ ነው የሚጠራው። ሶ ማክሲመም ሎድ ፋክተር ስንት ነው? ወደ 7.5 ነው ለስቶሊንግ። ማክሲመም ፖዚቲቭ ሊሚት ሎድ ፋክተር 7.5 ነው። ስትራክቸራል ፌሊየር ፖይንት ወደ 11.25 ድረስ ነው የሚሄደው። በኔጌቲቭም በፖዚቲቭም እንደዚህ። So the region AB is stall region. So stall ምን ማለት እንደሆነ ቅድም already define አድርገናል። V stall is equals to, you have to specify V stall from that equation. So የተለያዩ ፖይንቶች ምን ስያሜ እንዳለ እያንዳንዱ ላይ ያለው ፖይንት ከዚህ ማንበብ ትችላላችሁ። The flight velocity corresponding to B is the stall point. Okay, is V star ወይም V stall ብላችሁ መያዝ ትችላላችሁ። And which is related is N max with CL max. ከዚህ በፊት CL max ነው የምናውቀው። አሁን stall velocityያችን N max over CL max አለ። ሌሎች ፓራሜትሮች የነበሩ ናቸው። ምንም የተለየ የለም። So stall is related with CL max ነው. So now it is also related with N max. In the Venn diagram, line CD represents high speed limit. CD means which line? You can see CD from here. Look, line C is here, D is here. This region, C to D is our velocity boundary. Velocity will not exceed that point. Okay, so if we exceed, it immediately causes the structural damage. ለምን unstable የሆነ ፍላይት ይሆናል። Okay, so that dynamic pressure is higher than the design range for the airplane at that point. Okay, እዛ ባውንደሪ ስፒድ ካለፈ ዳይናሚክ ፕሬሸር ኢፌክት ይመጣል። የዳይናሚክ ፕሬሸር ኢፌክት ምንድን ነው የሚያመጣው በኤርክራፍት ላይ ብንል፣ አንደኛ ኤርክራፍት ፍላተሪንግ፣ እነዚህ የተለያዩ ቫይብሬሽን ታይፖች አሉ አይደል? አንስታቢሊቲ ኦፍ ኤርክራፍት፣ ፍላተሪንግ አለ፣ ዳይቨርጀንስ አለ፣ ኦኬ፣ ኤልሮን ሪቨርሳል አለ። ኦኬ፣ ሶ ዋፌቲንግ፣ ዳይቨርጀንስ፣ ፍላተሪንግ ዲስ አር አንዲዛይረብል ኮንዲሽን ኢን ዘ ኤርክራፍት፣ ዳር ኮንዲሽን ኦፍ ቫይብሬሽን። ኦኬ፣ ስለዚህ dynamic instability of aircraft will happen. Okay, so we have to so any one of these phenomena in the combination with high dynamic pressure could cause structural damage or finally failure, so that we have to bound it. So now let's take some example for the following aircraft data. Compute clean stall speed, just stall speed, B maneuvering speed, which is design maneuver speed, C limit and ultimate load factor, the stall or load factor, carbon Venn diagram, sketch the Venn diagram itself also. So these are the questions. Weight is given, which is about 686,700 Newton. That is maximum takeoff weight. MTW means maximum takeoff weight with full of fuel. Another area is given for narrow body aircraft is considered here. Wide body and narrow body aircraft maximum lift coefficient in the clean configuration, CL max is given. Density at sea level given, positive limit load factor, N limit plus 3.8, and negative limit load factor ተሰጥቷል minus 1.52. ስለዚህ ይሄን በመውሰድ የተለያዩ አንደኛ clean stall speed, that means it is at N is equal to 1, it is called clean stall speed. Okay, so for the level VS1 W, so that VS1 is equal to 2W because N is 1 times rho SCL max. ስለዚህ ያን ዳይሬክትሊ አፕላይ ማድረግ ከዚህ የምናገኘው ምንድን ነው? VS1 which is equal to 151.8 kNOT or 78.01 or nearly 78 meter per second is the clean stool speed at n is equal to 1. Maneuvering speed, velocity at A, at point A, so which is the design maneuver speed, another term, which is VA times, VA is equal to V clean stall speed times the positive limit load factor. Positive limit load factor, so which is given 3.8, so that simply we can multiply it with the stall speed. So that gives us 152.2 meters per second. And limit and ultimate load factors, the load factor n plus is given, n minus is given. So the ultimate load factor can be obtained by multiplying safety factor. Considering safety factor 1.5, can safety factor be less than 1? Safety factor. Now, load factor ምናምን ብለው ነርሱትና safety factor can it be 1.5? Can it be 0.5? Why? Load factor ምንድነው? Ultimate load by design, right? That should always be greater than 1. It can be 1 if the operation is simplified. It can be 2, 3, and especially for the construction equipment, it can be 8. For underground mining, it can be 9, 10. For road construction, it can be 7, 8. So that is always greater than. So taking the safety factor 1.5, the ultimate load is 1.5 times 3.8, which is equal to. So we have given limiting load factor already given. What we are calculating is ultimate load factor. So the ultimate load factor is limit load factor times the safety factor in the negative as well as in the positive. So you can put it. The stall or load factor VN diagram, how we can find n stall, actually what we call it as n stall at stall velocity actually. N at stall velocity we can say. So this is equal to L max divided by weight. So L max is half rho V square SCL max divided by weight gives you n stall. So in the clean state, n stall is 1, okay? But you can actually substitute all the values, then you can get n stall. So to sketch the VN diagram, what you can do, draw the horizontal axis using the given velocity. Velocity is given, so the horizontal axis is velocity axis. Again, you can draw the vertical axis using the n values. So just use n values for that. Put the stall curve, that is upward opening parabola. So you have a horizontal axis, which is V, and you have a vertical axis, which is N. So you have 0 point here. Then what you can do, just draw this type of graph. Again, here is even negative. You can draw like this. Then specify the limit load factor point. limit load factor 3.8 is the limit load factor. You can draw it like this. Here, limit load factor is minus 1.5 something is there. So like this. Again, ultimate load factor point. Ultimate load factor point will be somewhere around here. By multiplying it by 1.5, the safety factor. So you can take this points. So negative limit line, ultimate lines, negative and positive ultimate line. Then the speed, the A speed, the C speed. A speed is the speed where all those constant and is equal to 3.8. Design cruise speed, dial speed. Again, never exceed speed. Never exceed speed somewhere around it. Never exceed speed. The CD line in the previous flow, the CD line is never cross. So the speed should never exceed that point. So you have to put all those points and sketch the VN diagram. So finally, only the positive parts are there. Actually, for the negative also there. I didn't sketch the downward parabolic curve. So the positive one is given there. So this is your VN diagram based on the calculated values for particular aircraft. It is this VN diagram works only for particular aircraft. It will not work for different. Airbus has its own. Fighter aircraft has its own VN diagram, and they are very different. Okay? So the pilot must follow that VN diagram, and on the working manual of aircraft, it is there. So this is all about today's class. Maybe in the next we'll see ብትችሉ እንደው ደስ ይለኛል ብትችሉ ነገ ምክንያቱም የሆነ የስራ አንድ ሰዓት እንችላለን ለመስላቸው ለሚቀጥለው የሆነ ተማሪ የተፈተኑበት ሰዓት እና አምስት ተጨማሪ ሰዓት አቻለ ፈልግ እና እንደዛ ለማድረግ ብትችሉ ነገ لما سافرت استويت يعني كنترول الفرق ما نفسه من يشتغل يلا من Please have to image lectures. I would like to listen. Like I mentioned, material I think this is enough for today. The Sitama Kakaruna Nigaros.